To you by Dlubal Engineering Software. Today's webinar is about analyzing glass structures with RF glass. It will be presented by Chelsea Jennings and myself. My name is Walter Rustler. Before we start with the webinar, I'd like to give you some brief directions how to work with the webinar software for those of you who are here the first time. The webinar software has a little dialogue, and you can adjust there the microphone and speakers by pressing on the settings button. And you also may use the chat box for questions. Please keep them short. We'll try to answer them at the end of the webinar. And if we are not able or run out of time, we will follow up by an email. If you want to hide the dialogue, you can use the red arrow button that will minimize the dialogue. Before we start with a live presentation, I'd like to give a brief introduction into the concept of RF glass. In general, you will usually model a entire structure in RFEM that includes steel and concrete and timber parts or various other structural parts. In there you might also model individual glass surfaces. You may use them in the global analysis in RFEM for load distribution or just to include the self-weight of the glass surface into the global analysis. When looking at the glass surfaces, you will have to do this in the RF glass model, and in RF glass, in the module RF glass, you will extract or isolate the individual surface from the global analysis and take a closer look at there. So we do this because in RFEM we use different finite elements than we use in RF glass, and will build a more complex, a more realistic model in the RF glass module. We'll take a closer look at that later on. In the module RF glass, the geometry and the loads are imported from the selected RFEM surfaces, and we are able then to build up the individual structure of each glass surface in so-called layers. The layers can be made from glass, gas, foil, and it can be the glass surface can be made from a number of different layers, as typically a regular glass surface would form. You specify the materials and the supports in RF glass, since we isolated it from the general RFEM model. And we also have special dialogues to enter additional climatic loads in case of insulated glass. With this information, a specific 2D model or 3D model is created automatically in the background in RF glass, and the RF glass module takes over this job, and you don't have to model this yourself inside RFEM. It is very demanding and very time consuming. After this, or before I go on to the next slide, maybe here is another preview. We'll see this then later on also live, of the climatic load parameters input in RF glass, and also we'll see later on live a preview of the packet of solids that is created from each glass surface as a so-called submodel by RF glass. So we analyze basically a 3D solid surface model combination from each glass surface that is picked from the global analysis model in RFEM. The results in RF glass are then presented in tables and in sections. You see a cut view of the glass packet with the stresses in each layer, and you can see this for each load group or summer and winter load condition. Additionally, you have a specific view of the graphical representation of the results in the main RFEM window with a specific navigation tree that allows to address each type of stress at each surface, top, bottom, middle, wherever you want to look at it. Additionally, you can also print the results graphically as usually in RFEM. So at this time, I'd like to hand over the controls to Chelsea, and she will show you in the first example the work in RF glass, and then I will continue with another example. Chelsea, it's your turn now.
Thank you, Walter. Hello, everybody. I'd also like to thank you all for joining us today for this webinar. Now that we've had a nice introduction to the program, I'd like to go ahead and start our full presentation with an example of how to work in RFEM glass with laminated glass panels. So to start, I have my glass panel defined as a surface in RFEM. As Walter mentioned, your panels can be a part of an overall structure model in the program. For simplicity, I just have the one surface created. So here I have a surface that's 60 by 140 centimeters, and it's defined as a glass type, and I have my thickness set so that for when you do additional analysis in RFEM, the main program, your self-weight will be considered appropriately. In addition to the surface, I have also defined a few load cases and combinations. I have self-weight, a snow load, an additional pressure load, and then a few load groups for the analysis. And so now I can go ahead and open up the add-on module, RF glass. And here we are in the first section where you define which surfaces you are going to perform the analysis on. I just have one surface, so it has automatically selected it. But when you set the surface or the surface type as glass in RFEM, that lets the program know, RF glass know that that's what you want to design. So it will select those surfaces automatically. Below that, you see our table for where you assign load cases or load groups and combinations to your different designs. So I'm going to select these first three load groups for my ultimate limit state design. And you can also apply the design situation for individual load cases and load groups as well. In the serviceability limit state tab, I'm going to add my fourth load group for the design. And here we have our action combinations, which can be applied as well. So moving on to the next section in the navigator here on the left, we have our layers tab. And this is where you'll define the individual layers of the panel. So starting with a glass layer, you can define or select a material from our material library that we have available. And for each material that's listed below is a list of material properties available for your information. So I'm going to select this thermally toughened float glass and define the thickness. And then the rest of the material properties are automatically imported to the table from the material library. The next layer will be my foil layer. And going back into the material library, based on what you have selected in this first layer for your layer type, your material category is automatically filtered to that type of material. So I'm only seeing now foil materials. Selecting that, and for my thicknesses here, we have a list of standard thicknesses from the manufacturers. and then I will just have one more glass layer with the same thickness, and it has remembered my previous entry. So it can help if you have asymmetric or repeating layers. Below you can see here a diagram for the selected materials and the selected layers. And to the right, for the individual layer that you have selected in the table, you can see the surface weight. And below that, the overall thickness and weight of the entire panel with all the layers. Next here, you can activate 3 different types of factors, starting with the partial safety factor gamma M, which will affect your allowable stress. And this can be adjusted here in this dialog. I'll come back to this in a minute and explain some of the other things available there. We also have modification factor K mod, which can be adjusted in that same table that I just showed. And when this is selected, over here in your navigator on the left, you see a new section called load duration. And this is the table where you apply the load duration class for the load cases. And the coefficient will change depending on your selection, and this is what you can define. I'll go back to that dialog, and those are the coefficients that you define here. Lastly, you have a construction factor, which you can adjust just right here easily. So going into the next part for our input data, you can define the supports around the panel. So I'm going to apply line supports on all 4 sides, which you can type in or you can select graphically from your model in RFEM. There are available hinge types, and you can see in the diagram to show where the hinges are located. I have this one in both the glass layers. And below you can also manually define your restraint settings and apply rotation and where exactly the support is located on the layer for user-defined setting. We have the same options available for nodal supports. And the next table is for boundary members, if that applies to your model. If you have some beams surrounding the glass panel, you can define those here. Next, if you have selected serviceability design, this is where you enter in your surfaces to be included in that, and you can define a manual reference length or use the one that's given. So this is all of the input data that is necessary for a laminated panel. Next, I'm going to go into the details and show you a few more setting options for the program, including the calculation parameters. So first here, you can decide which stresses specifically you would like to calculate. You can choose a different setting for the middle layer that's independent from the top and bottom layer. So here with foil, I can just calculate the shear stresses for the foil layer. If 2D calculation is selected, you have options here for your plate bending theory. And also below you have options for how to determine the equivalent stresses. In the Designs tab, this is the one we had a quick look at. Last thing I didn't mention was you can adjust here your deflection limit. In the Options tab, we have some options for displaying results. This is to display them directly in the model, and additional options are available for displaying results in the printout report, which I will show in just a little bit once we finish the calculation. When shear coupling of the layers is considered for laminated glass, you can choose to run either 2D or 3D analysis. And we have a third option here for if you can set a limit so that if the value of this term reaches it, then the calculation is done in 3D, otherwise in 2D. And this term includes the shear modulus of both the glass and foil layer and also the thicknesses of both. I'm going to run a 3D calculation for this example. One last thing I'll point out is if you're working with insulated glass, this section will become available and you can define a secondary seal around the panel. So I have all of my desired settings and my input data ready, and I can go ahead and run the calculation. And so, as Walter said, the calculation of the surfaces is local, and the individual surfaces are calculated separately without influence from a model in RFEM. So here we have our standard setup of our results display that appears in the navigator. Our first table available shows the maximum stresses by load case. And so you can see here we have the stresses grouped by load case, and in each load case you have your normal, shear, and your principal stresses, or whatever you have chosen to calculate in the detail setting. Based on what you have selected in the table, you have a corresponding diagram below which shows your stresses throughout the layers. You can also see in the table which layer, which surface, and which layer and which part of the layer, the middle, top, or bottom, the stress is referring to. We have a similar table for the stresses by surface. I just have one surface in this example, so it's just going to give me my maximum stresses, but it would be grouped in the same way as the previous table if there are more surfaces. In this next one, we have detailed results which show you the stresses for each calculated point in the surface. In our last bit of output result, we have the maximum displacements. And so here you can see your maximum displacement and your overall ratio with the limit. The program also gives you a nice little parts list, which will be included in your printout report documentation. And so I can go ahead and open the documentation that is produced automatically. And so here's the printout report, and we have our RFEM data, and this will contain any analysis that has been done in RFEM. And then below that we have glass here. And you have your input data and your results data. And this is including all available tables, and it's only taking a couple pages, so it's no problem to include all of them. But if you have a more complex project and many cases, then maybe it's value to you to select only a few different tables. So I can go into this option here, and you can select which input data you want to show and which results you would like to display to kind of compress it and give you the information that's important to you for your documentation. And this is, as usually, customizable for the user for all of our programs available. So this concludes my example with working in RF glass to design laminated glass. And at this point, I'll go ahead and hand Walter the presentation, and he can continue and give us a demonstration on working with insulated glass and some other features in RF glass. Thank you.
Thank you, Chelsea, for this nice example. And I'll continue with RF glass and an insulated glass example. I've prepared here a small example with actually two load cases, self-weight and wind pressure. It's nothing spectacular. It's just one load on there, and I have a load group with both loads combined. I start the module RF glass, and inside RF glass I select the one surface that I have, and I add the load group for the ultimate limit state design, and for the serviceability limit state design I add the load group without safety factors. So far it's all the same as before. Now we come to the layers, to the glass layers, and here I define first a glass layer of type glass with thermally toughened float glass, and also I select here a thickness of 6 millimeters. Next I will select gas as a layer. And in case of gas, there's a different material library that includes all the typical gases. Typically, argon is used for such glass surfaces. And the thickness of this layer will be 20 millimeters. Next layer will be again glass. This time I select only 4 millimeters. And I will combine it with a foil. Similar as what Chelsea did before, with thickness of 0.38 millimeters, and another final glass layer with thermally toughened float glass of 4 millimeters. So you can combine laminated glass with insulated glass or gas layers, and in case of this gas layers, then we'll have automatically available climatic load parameters, which we'll take a look at it later. I want to point out you can import export with Excel here. If you have such layers in an Excel table, you can import and export it from there. You can also save your own library from what you entered here, and then later on open those libraries again and apply them for fast input. I'll activate the partial factor gamma m. Typically for thermally toughened glass, this could be 1.5, this gamma m. If I work with thermally toughened glass, I don't have to have a modification factor usually, but if you want to also work with modification factor K mod, then the load duration comes available as seen with Chelsea's presentation. I don't need it in that case. Construction factor as well I don't need. Let's take another look at the other options we have here. Serviceability limit states will take for the characteristic, frequent and quasi-permanent condition those limitations. In the options, I want to activate the saving of the created substructures that we want to take a look at it later. I may or may not consider coupling. Some codes allow it, some codes don't allow it. And in this case, with this configuration, I always will have to use a 3D model. So we'll take a look at this later. Also, I may or may not include the secondary seal. If you don't have any secondary seal, then the stiffness of this seal will not be taken into account. This way you can model it in the 3D model. As stresses, typically I only need sigma 1 and sigma 2, and I check off the other ones. Maybe one last option to make the calculation a little bit faster. I work here with only two load increments. This may have an effect on the results, so as well as the mesh density and the number of load increments, it is an important little control that you can switch on and off or influence. You may try out yourself whether it has an influence on the results or not. Typically, we recommend to have a reasonable mesh density, which is dense enough for the structure. You can find that out by gradually increasing the density, and if the results significantly change, then obviously this has an effect. If not, then you may also work with a more coarse result, but also take into account we're working with finite elements. There might be singularities, so it is mandatory to really take the results at a location where no singularities have an effect. And if you have a singularity and you increase the mesh density, of course the results will change. Also, this seals, the stiffnesses of the seals and the materials, everything is very sensitive in the matter of glass analysis. Choose those things carefully and figure out whether how those changes have an effect. Okay, next we'll talk about supports. Again, I will take all 4 lines as supports. Here I'll choose the type 2, which is only supporting the internal side, the internal line. Also, it may be recommended to choose here user-defined and then set here especially or specific spring constants, because again singularities might happen, and typically a more elastic support condition is better for finite elements than really rigid support conditions. But you have here all options and you can choose yourself. Also, those things can again be exported and imported from Excel. Nodal support and boundary members are not in this model. Maybe some information why we have those things. You can also model a supporting beam along the edge of a surface and then only support this beam that carries the glass on certain nodes. This then gives you a more realistic model of the stiffness of such a support condition for the glass, which the beam is a support condition for the glass. So there is a little bit more freedom in how to model those things. Next, we take a look at the climatic load parameters. Those parameters will have an effect on the loading of that comes from the internal pressure when the temperature increases or decreases, or you go into different altitudes. Typically, there's a number of temperatures you can adjust. I enter here 20 degrees for a manufacturing situation, and for mounting situation 40 degrees. So we have a difference of 20 degrees, and I do the same thing for the gas, and the internal temperature should be maybe also 20 degrees. The altitude at manufacturing should be 300, and at mounting as well. And this was for summer, and then we can use the same for winter. So not the same, but of course a different mounting temperature at the end. So we have altogether a decrease in temperature of -25. The altitude I choose again with 300 meters. So all these parameters will be the input for the loading of the sub-model that is created after we start the analysis. So I set now those parameters in such way that we kind of follow the DIN 18008 code, which will be coming out later this year, or most likely next year. So these are maybe recommendations that come from a code or that you have from your contractor or other codes maybe. You also have the option to distribute the loading to the external or the internal glass side. The self-weight of the structure is naturally distributed as is on the individual glass layer. But if you have maybe another quote self-weight external load, you can decide here with those percentages where they will apply. If you have a rectangular surface and on 4 lines supported surface, glass surface, but not type 1, but not type 2 as I have it, but in all glass layers are supported. Then you can use the calculation according to the TRLV, which is another guideline for analysis, and this option will then be available. At the end, we'll select the surface 1 for serviceability, and now we are ready to run the calculation, and I start the analysis. So what happens now in the background, all those submodels are built and analyzed for summer and winter conditions. We see here now in the graph 2 load steps, so there's somewhat of a kink. After the first load step reaches its equilibrium, and altogether now I think we will analyze a set of 4 load groups after one each other, which include also the analysis of the submodels. And then we get the representation of the results, hopefully, and that will be similar to what we've seen from Chelsea. So one more iteration. So now we see here load group 1 for summer, sigma 1 and sigma 2. And we see here, as Chelsea said, bottom and top side, the most controlling, the biggest stress that happens and where it is and which stress point and so on. Same thing for winter, and then a summary with the maximum stresses. Same thing by surface, and if you want to, you can take a really detailed look in all points. Graphically, we can look at the results as well. We see here the glass layer number 1. We see here the navigation tree, load group 1 for summer, sigma 1, sigma 2, and then the ratio, utilization ratio, which is rather small in this case. Same thing for the bottom. And then the glass layer number 3, remember we had layer number 1, then there was gas, and gas has obviously no tension or compression or stress. So we have layer number 3, and we have on the top and on the bottom, and then we have the last layer on the top and on the bottom. We also get the same thing for the winter load cases, and at the end we get also the deflection of the glass surface. So if I want to print such graphics, I just select what I want to print. I go to print, for example, to the printout report, the window filling. In this case, I'd like to use the whole size, the whole page height. I get already a header for the picture. I press OK, and it will open my printout report, and I get the same picture here. When I do this next time, I will have the option, for example for sigma 2, the option to print it but not opening the printout report. I can just drop it into the printout report. This makes my work much faster. I just select what I want to see and I say print and so on. Once I'm done with my printing, I can select again show printout report, and I'll see the result of what I have printed in printout report. Maybe one last hint. If I select, multi-select all graphics, right click and go to properties, I can say, okay, maybe I only want to have 50% of the page used for one graphic, and maybe I want to start with a new page with the first graph, and I get a nice picture of all those glass panes, all those layers, 2 graphics on one page. So at the end, we also want to take a look at the generated submodels. So my name is class webinar sample 2. And if I go to the folder where I store this file, I find two new files. One is class webinar sample 2 RF class W1 for winter and S1 is for summer. So by double clicking on it, I can open it. And we can take a look at the constructed 3D model of this before very simple surface. So it created a set of solids. There's one solid or two solids actually for the first exterior glass pane. Then we have this blue solid which is made, or which is the air. Then we have again two solids for the next glass layer. Then there is a very small solid for the foil, and again the next packet for the final glass layer. So all those things, including the supports, are created automatically by RF glass. Also, we can show the loads. For example, the pressure load, in this case, is simple. The load group, the climatic load, is then created as an equivalent load. This is now for winter, so it's pressure, and if it's for summer, it should be expanding, so it will be pulling apart the glass surfaces. So this is how this model works. You can look at it. You even, if you want to, you can even analyze those submodels. They are available if you save them, and then you have a real 3D model of those surfaces. Okay, I think I'm through with this presentation, and we are ready to take a look maybe at a few questions that we have here, and it will take me some time to read them, I guess. Okay, there are quite a few questions. I'm not sure if we can address all of them, but let me see what I find here. There's one question: with which code do you effectively do the design? Well, there is no real code that you can select in the module. It is more or less a stress analysis with requirements on limited stress and factors on the load side. Codes in glass are not so many available. We have this TLRV, and there will be, as I said, this DIN 18008 coming up hopefully soon. And so far there is also, to what I know, no Eurocode that is available. So no controlling code, or no code which is really acceptable throughout the world, I think. What is the difference between line supports and boundary members is another question. If you have a line support, it is just like a regular line support in RFEM. If you have a boundary member, it is also some kind of support, but the stiffness then depends on the member, on the stiffness of the member. And the member must be supported somehow, either by being connected to another member or by having a nodal support. So it is just a little bit more freedom in how you model the support conditions for each glass pane. Do the K-mod factors affect the PVB module's value? The K-mod does, to my knowledge, only affect the limiting stress of the layers in the glass. So we do not do really a stress analysis of the PVB. So I don't think it will have an effect. But in fact, I cannot really answer this perfectly now. I think we will have to follow up on an email with these questions. How the gas argon can transfer pressure load from external glass surface to internal? Well, you have to imagine that there is a enclosed gas, what is it, volume, and if you compress it, this system will somewhat have an effect on the other surfaces that are boundaries for those volume. And so in this case, the pressure will be transferred from one part to the other one. In this module here now there's a simplified equivalent model that makes equivalent loads. In future RFEM versions, we keep on developing, of course. It will be also, there will be a special gas element, gas solid element that will have even better qualities how to mathematically model such situations. It's not such a simple thing, but now it is in such way that we apply external equivalent loads to those boundary surfaces to model those loads. Is it possible to calculate the stress due to cold bending of the glass? At this moment we have no pre-stress or initial stress in the structure. So when we start analysis, the stress is 0, and only through the external loading we get this stress. So if there is any stress already in the structure, it's not considered at this moment. But it will be possible in future to also analyze bent insulated glass models. So if you have a insulated glass surface that is not 2D, not plane, we will be also able to analyze it. In case of deflection checks, how to check when you have panel members at the edges? Well, what we do now with the deflection check, we will take the longest edge of the surface, which is kind of our reference length, and then inside RF glass you can set the limits which are referring to this length. And for example, length divided by 200 is the limit of the deflection. And then we look for the maximum deflection we have inside the glass pane, and then compare this value to this limiting value. If you like to set, if it happens, accident, or if it happens where a member is, then this value will be there. But most typically, I think if there is a member in the structure, it will add stiffness, and the deflection there will be naturally smaller than in the other parts of the surface. So it's rather unlikely that this part will be then the controlling one. Okay, I think we've been through most questions I can quickly understand now in this short time we have here. We will definitely follow up with all questions that are maybe not enough answered. If you have other questions, just keep on sending them to us, sending them to info@dlubal.com. Before we finish this webinar, I'd like to go back to the presentation and point out some other things that I'd like to share with you, because we have further information on our website. We post frequently things on our social media pages, Facebook, Google+, follow up also YouTube with videos, Xing or LinkedIn. And what I like to point out especially is the Dlubal blog. You find the link on our website. In there is daily postings with small hints how our software works, what can be done to find certain switches and options, maybe things you haven't thought about it or didn't need so far, but it's good to read through those little short stories. Won't take a lot of time, and once you have a use for it, you might remember and you always can go back to the blog. Contact information, I think, is clear. I don't have to repeat. And one last thing I would like to point out, the next webinar will be on October 10th. It will be also posted on our website and on our social media pages. It will be about thin-walled steel structures with shape thin and RFEM LTP. What we'll do is something like create a arbitrary thin-walled section, import it into RFEM, do an analysis there, and then have a stress and stability check with RFEM LTP, which is a lateral torsional buckling program, or actually stability analysis program that includes buckling and lateral torsional buckling according to theory second order. Registration can be done, as always, over our website. I'd like to thank you for the time you spent with us today again, and I hope it was useful and informative, and I wish you a nice day and see you hopefully soon again on this channel. Bye-bye.